Okay, so let me remind you what we have done during the last session. We spoke about the electrostatic equilibrium, and we said a conductor is in electrostatic equilibrium means there is no net flow of charges inside the conductor. The free electrons, we said conductor has free electrons that can move around, but there is no net flow of charges in any direction. And we said the implications of this are a number of implications. First of all, we said the electric field inside the conductor at any point inside the conductor is zero. Okay. Second, we said all the charges, the extra charges on the conductor will go to the outside surface of the conductor. So the extra charges, they all go to the surface. Okay. And we, what else did we say? Yes, we said that the electric field outside the surface of the conductor is always perpendicular to the surface. The electric field outside the surface of the conductor is always, so inside it's zero, outside is perpendicular to the surface. And the electric field outside the conductor, the magnitude, we used Gauss's law and we proved that it's equal to sigma over epsilon zero. Just immediately outside the surface, it's sigma over epsilon zero. Obviously, if you go farther away from the surface, then that's not valid anymore. But immediately outside the surface of the conductor, the electric field is sigma over 2 epsilon 0. What else did we mention? Okay. Yes, we said that any 2 points on the conductor, they have the same potential. So if you measure the voltage at any point on the conductor, it will be the same voltage. Okay, so there will be no difference of potential or voltage difference if you are on any 2 points on that conductor. Okay, and we have shown that if you take, for example, a spherical conductor, the electric field is zero inside the conductor, so you can see the electric field is zero here, then it's kq over r squared. This is given by Coulomb's law outside the conductor. But the voltage or the potential, the electric potential, is constant inside the, it's not zero, it's constant. Okay? And it happens to be equal to the potential at the surface of the conductor. But when you go away from the surface of the conductor, you can see that the potential is now kq over r. Here it's kq over r squared for the electric field and kq over r for the spherical conductor. Okay? And last time we started by solving this problem. Okay? And we said if you have two spheres, two conducting spheres, one has a charge, one has charge conductor, okay? All right, so after connecting the spheres, the charge on the large sphere is Q1, on the small sphere is Q2, okay? And we were asked to determine the ratio of the potential on the spheres, V1 over V2, the ratio of the charges Q1 over Q2, and the ratio of the electric field magnitudes E1 over E2, and also the ratio of the surface charge densities, ρ1 over ρ2, okay? So, the first thing we did, we said, since now the two spheres are connected, so the whole thing, the two spheres and the conductor between them is the same conductor now because they are touching. The potential, or the voltage, is going to be the same everywhere. And we used this to solve, we determined, let me take this out. Okay, so we said V1 is equal to V2, but let me write it. V1 at the radius R1 is equal to V2 at radius R2, okay, because they are touching. And so if we write the equation for the voltage, that means, so this means K Q1 divided by R1 is equal K Q2 divided by R2. So the K's will cancel and we obtain that Q1 over Q2 is just equal R1, so Q1 over, R1 over R2. Okay, so this is the this question here. So V1 over V2 is 1, so V1 over V2 is 1 because they are equal. Okay, Q1 over Q2 is R1 over R2. Okay, the next thing is the ratio of the electric field magnitudes at the surfaces. Okay, so at the surfaces, this is a spherical conductor. We had the equation before. We used Gauss's law and we determined the electric field is electric field at the surface 1 is KQ1 divided by R1 squared. So this is electric field at radius R1. Okay, electric field at radius R2 of the second sphere is KQ2 divided by R2 squared. Divided by R2 squared. So if we take the ratio E1 over E2, so this is KQ1 over R1 squared divided by KQ2 over R2 squared. So we will get this Q1 over Q2, and this is R2 squared divided by R1 squared. We know Q1 over Q2 is R1 over R2. So we replace it, we can replace it here. So this is equal R1 divided by R2 times R2 squared divided by R1 squared. So this is going to be R2 divided by R1. So we can say E1 over E2 is equal R2 over R1. Okay. Okay, so we have determined that Q1 from this, Q1 is larger than Q2, Q1 is larger than Q2, and we can determine from this that E1 over E2 is the smaller radius divided by the larger radius. That means E1 is less than E2. Yes, so E1, yes, is less than E2, the electric field at the surface. Okay, the last thing we want to do is the ratio of the surface charge densities. Okay, so we need to calculate the surface charge density. We said all the charge, extra charge, will be on the surface. Okay, so if we divide the charge on the surface by the surface, we can get the surface charge density. So let me write it here. Rho1 is going to be the charge Q1 divided by the surface of the sphere, which is 4 pi R1 squared, and Rho2 is Q2 divided by 4 pi R2 squared. So I can divide Rho1 by Rho2. Okay, so the 4 pi will cancel, and we will have Q1 over Q2 and R2 squared divided by R1 squared, and we know Q1 over Q2 is R1 over R2. So we end up with it's equal to R2 divided by R1. So again, sigma 1 or sigma 2 is equal to R2 over R1. What does this mean? It means that the charge density for the large sphere, charge per unit area, is smaller. So the charge per unit area, so this is the charge per unit area here is Rho1, the charge per unit area here is Rho2, and from this derivation we find that the charge per unit area Rho1 is less than the Rho2. Okay, clear? By the way, this problem was given in the final exam last year. They were asked, I think, only for E1 over E2 or V1 over one of these, and they were asked to solve for one of this. This was one of the problems in the final exam. Okay? So, I think we did everything correctly. So, Q1 over Q2 is R1 over R2. E1 over E2 is R2 over R1. So, so here, E1 is less than E2. This is electric field at the surfaces. Okay, we determined Q1 is more than Q2, and we determined that ρ1, the charge per unit area, is less, ρ1 is less than ρ2. Okay, so from this we can say the electric field is strong when the radius is small. Okay, so notice the electric field E2 was larger than E1, and the field is weak when the radius is large, however, same thing. But also we notice that the charge per unit area for the larger sphere is smaller than the charge per unit area for the smaller sphere. Okay, so let me go to the presentation mode for this. No, it takes too long. Okay, so if you take a conductor that has a spherical shape, the charge per unit area at any point on the surface of the conductor is going to be the same because of symmetry. How about if the shape is not symmetric? Like, for example, this shape here. Okay, so here you can see this is not a spherical, so this is this radius of curvature is much more than the radius of curvature here. Okay, so the charge per unit area is not going to be the same. What do you expect the charge per unit area to be more on the smaller curvature or on the larger curvature? Charge per unit area smaller. We just have proven it in the previous case. We've seen that for the smaller sphere, now the two spheres are connected, so it's like the single conductor. The one that has a smaller radius has higher charge per unit area than the one of the larger radius. Okay, so this is what we're saying here. When the net charge placed on a spherical conductor, the surface charge density is uniform. However, if the conductor is not spherical, the surface charge density is high where the radius of curvature is small, and low where the radius of curvature is large. Okay, so this is the another observation that we can extract from the previous example that we have done. So the surface charge density is greatest where the radius of curvature is the smallest. Okay, so that explains when the metal piece was brought to establish, I don't know, maybe 600,000 volts between the car and the metal, you have seen the spark coming out of the sharpest point in that metal, because that's where you have the strongest electric field, and that's because it has the highest charge per unit area at that very small curvature, and that's why we see the spark coming out of that point. Okay, one more implication. Let's assume we have a cavity inside the conductor. A cavity, تجويف يعني, and it's empty, okay? And there is no charge inside this cavity. And any 2 points A and B on the cavity surface must have the same potential. We have said the conductor, any 2 points, they have the same potential. So what does this mean? So if you write VB minus VA, it's the integral of A to B E dotted with the S. We have seen this. This is equal to 0 because VB and VA are equal, so this is equal to 0. Okay? Since this is 0 for any path between A and B, remember the electrostatic force is a conservative force. So it does not depend on the path taken, it depends only on the initial and the final position. We said, remember, we said a conservative force, like the gravitation force, the work going from A to B only depends on the position of A and B. It does not depend on the path taken. Same thing for the electrostatic force. The work done by electrostatic force does not depend on the path taken. It only depends on the original position and the final position, A and B. Okay? So that means that E dotted with the S is equal to 0, okay? Hence, the electric field has to be equal to 0. Everywhere inside the cavity, the electric field is 0. So, we can conclude from this that the cavity surrounded by a conducting wall is field-free or zero electric field region as long as no charges inside the cavity are placed inside the cavity. So, if there is no charge inside the cavity, okay, the electric field inside that cavity is 0. And this is what we have observed for the car. The person in the car, he did not feel anything, okay, the very strong electric field outside the car, because he was inside the cavity, and inside the cavity there is 0 electric field, okay. So this phenomena is used in Faraday cage. It's called Faraday cage, which is a conducting material, either solid or a mesh, surrounding the interior space. The demo that we had, the teacher, when he placed a radio and he put a mesh around it, there was no signal coming from the radio, because now the radio is in a Faraday's cage. There is 0 electric field inside, so there is no signal, because the radio signals are electromagnetic waves. So these electromagnetic waves cannot penetrate the cage. That's why when you go into an elevator with a mobile and you're talking, sometimes you lose the signal, because you entered a Faraday's cage. Inside the Faraday's cage, assuming the elevator is a conductor, there is 0 electric field inside it. Okay? A Faraday's cage is used to protect sensitive electronic components from surrounding electromagnetic interference. So this can be used for protecting some sensitive components in electronic devices. Okay? Maybe I have time to at least to show you this. This is, I want to show you Faraday's cage this is in the Boston Museum of Science, and okay, so let me stop it and increase the volume as much as possible. Okay, all right. So there is a Van de Graaff generator, 2 huge Van de Graaff generator. This lady is inside a cage, a metal cage, and let's see what will happen. So you can see the strikes, oops,